as I was just saying, two different functions which have the same derivative will have almost the same graph. What do I mean by almost here? One of the graphs will just be a vertical shift of the other graph, right? They got to be increasing in the same places. They've got to be decreasing in the same places. So all I can do without changing that information is just sliding the graph up and down. So knowing the derivative of a function, I actually know lots about what that function could be. The only thing I really don't know here is what is my y-intercept? When x equals 0, what is the value of this function? I can't get that from the derivative. I can find lots of stuff. I can find out where it's increasing or decreasing, but I'm going to get a very different picture if my y-intercept is 0, or if my y-intercept is 2, or if my y-intercept is -4. Those are all different graphs. Well, that's the missing piece. I have the derivative of a function. I would like to know what function it started out as. And I know that there are infinitely many possibilities what that graph could be. So what I'm gonna do, step 1, I'm gonna try to find some possible solution, right? I know how to take derivatives, and as long as I think about it, I think I should be able to undo derivatives too. So I'm going to look for just one possible solution. Once I have that possible solution, the real answer has to be the solution I came up with plus some constant, plus some number. All I got to do then is just figure out what that number C has got to be. That's it. So this process of undoing a derivative, this comes up all the time, to the point where we're going to give it its own name. So taking a function, calculating the limit of its difference quotient at every different x coordinate, we call that process differentiation. And the result of differentiation is the derivative of a function. Now we would like to undo differentiation. And for right now, we're just going to use our rules in reverse. So to undo the process of differentiation, we will use a process called anti-differentiation. And the result of anti-differentiation is the antiderivative of a function. Now, I need to be careful here. Derivatives are unique. One function, one derivative. But everything I was just saying in this lecture goes to show that antiderivatives are not unique. If a function has an antiderivative at all, many do, it will have infinitely many antiderivatives. All of them are differing by some constant. So here are a couple antiderivatives for the function f prime of x equals x. X squared on 2 is certainly an antiderivative of that function, as is x squared on 2 all plus 1, or x squared on 2 all plus 10, or x squared on 2 all plus 100, and so on. Why, even this function, x squared on 2 plus 7 eighths followed by 8 sevenths. Why did I pick 7 eighths followed by 8 sevenths? Because it's a prime number, and I think that's cool that a prime number could look like that. All of these are different antiderivatives of the function.